You split up the problem into two parts, because that's what we're talking about. Divide and conquer. Break up a harder problem into smaller pieces, and then tackle, prove each piece one by one, individually. Okay, so when you're trying to prove that two sets are equal, you break up the problem into two parts, and the first part you prove that one set is a subset of the other one. And the second part is you prove that the other set is a subset of the first. Okay? So let's see. So you have your two sets, set A and set B. So the first part of your proof, you show that set A is a subset. Remember that from when we're talking about sets. A is a subset of B, and for the second part of the proof, you show that B is a subset of A. Okay. Now you see where I'm going with this, and then once you've done that, once you've shown that A is a subset of B and B is a subset of A, now for them both to be true, there's only one way that these two statements are compatible, and that is that A equals B. Right? You can't have A as a proper subset of B, and B is a proper subset of A. That's just contradictory. That's just nonsense. Right? So the only way this and this, these two statements, can be compatible, both true, in other words, is that set A equals set B. Okay? So if you can prove A is a subset of B and B is a subset of A, then effectively you have proved that A equals B. Hope you follow that logic. Alright, so with that sort of grand strategy, how do you go about proving that a set is a subset of another set? How do you do that? Well, it's by definition of what a subset is, remember? So let's, how do you prove, like, how do you prove that B is a subset of A, for example? Well, you show that every member of B, now remember this sign here? It looks like a capital V, like this, with a sort of a little arc here. That's a common symbol in pure mathematics. It means for all, or for any. So for any x, or for all x, that's a member, for any member of the set, belonging to B. So in other words, for any member of set B, that member x will also belong to A. Right? So that's the definition of B, set B, being a subset of A. Right? By definition. So to prove that, we're doing this case, okay? So that B is a subset of A, you have to prove this. So for every member of B, that member will also be a member of A. Okay, that's this. Now the other way, prove that A is a subset of B, you have to show that every member of A, so for all Y belonging to A, implies that Y belongs to B. You have to show that each member of A belongs to B. Okay? Therefore A is a subset of B. So you got this. So this, to prove that, you have to prove this. And to prove that, you have to prove this. Okay? So in other words, to prove two sets A and B are equal, that boils down to proving this and this. Follow that logic? Okay? Now we like, in two sessions we'll actually do that. We'll actually take two sets. Now here we have not specified what these two sets are. We're just talking generally, right? Two sets A and B. But 2 sessions from now we will have two actual sets, two concrete sets. You'll know what they are sets of what. You're told what they are, and you're asked to prove that those two sets are actually equal, even though they look different. The way they're specified, the way they're written, they look quite different, but they're actually the same set. You know, and two sets are the same if they have the same elements. Okay. All right. Now let's see. Ooh, for almost 1.5. Maybe two and a half sessions now. So we're getting now onto a big topic. So sort of a new topic is clues, hints, suggestions on how to go about proving a theorem, your theorem statement. How do you do that? Because it's not easy often. You know, some theorems are pretty easy to prove, and and especially if you're very bright, you just go through it very quickly. But there are theorems and theorems, right? Some are really quite difficult to do. So how do you go about proving something? How do you prove a theorem statement? Often, I keep saying theorem statement. A theorem, strictly speaking, is the statement of what you're trying to prove, and the proof itself, and the whole thing. So there's two things: the theorem statement plus the proof. Strictly speaking, that's what a theorem is. But people get lazy and they just talk about the theorem, and what they're meaning is not the whole proof, but just the statement of the theorem. Okay, so I'll get lazy sometimes, and I'll just talk about this theorem, and what I'm really talking about is just the statement of the theorem, without the proof. I mean, usually the statement of a theorem is just a few lines, right? Whereas the proof can be pages, sometimes a whole book. Group theory proofs have been hundreds of pages, and one of the greatest intellectual achievements of all time for whole humanity, if you've followed my first course on finite group theory, has been the classification of the finite simple groups, and its proof involved, I think, something like 500 different mathematicians, and went to about, I think, 15,000 pages of journals. So huge, right? So anyway, so there are proofs and proofs. Some are easy, some are hard, and some are impossibly hard. Okay, so how do you go about proving something? So well, you need to get familiar with it, with the problem. So you try to establish a kind of gut feeling, like an intuition about the problem, of why you think maybe it's true. And one way to get a feel, because when you're starting, you're unfamiliar with the problem, right? You're more sniffing around, perhaps looking for patterns or something. So try and get a feel for what it's true. Now, well, this is I think it's implicit here that you're actually given the theorem statement. I think that's true. Now, if you're a research mathematician, it's up to you to create that theorem statement, right? That's a lot harder, and for that you're really sniffing around. But let's assume here you're more as students. So in other words, you're given the proof statement, and you have to prove it, right? So you work towards getting a feeling for an intuition of why it might be true. Okay. Now, how could you do that? Well, one example, one possibility is try various examples of it, maybe restricted examples of the general statement, special cases, if you like, and see if it's true. And you might do that for several cases, and that'll give you some experience that it's true. Okay, typically a theorem statement, will say that some object, some mathematical entity, whatever it is, I'm being deliberately vague here, but Well, last time I think I mentioned the object would be, as an example, a prime number. And so an object will have some kind of property, a certain kind of object, mathematical object, like a prime number, or the set of prime numbers, will have a certain property. I think you can probably see this first line, usually yes. And then you can show that with a few examples that property is there, that it's true. Maybe you might go hunting for a counterexample. You only need one, right? If you can find just one counterexample to a theorem statement, then that theorem statement is not true. Right? Just one counterexample is sufficient to kill a theorem statement. So you only need to find one counterexample. So often when you're trying to prove something, and you're not sure whether a statement is true or false, sometimes it's easier to go hunting for a counterexample initially, because if you find one, then you don't have to bother trying to prove it, right? So whether your strategy, often the hardest thing in proving something is the first step. Which direction do you head? Like, for example, do you try to find a counterexample first, or do you try to actually prove that it's true? And it depends. And like I say, theorem proving is an art, often requiring high intelligence and sometimes just sheer brilliance, and at some stage, sometimes just genius. Some proofs are very hard and very few people capable of proving it. Like some of the stuff, I've mentioned this name before, but in group theory, a guy called Thomson, reputed to be the greatest group theorist in the world. Some of the stuff he's done is just jaw-dropping, and very, very few other people in the world would be capable of doing what he's done. Right? Well, I can't get too far down in the present, in the second session, because you can't see it. So I'll stop there and then just continue straight on.